Okay, I don't remember exactly the title of the seminar, but it's something like this. So, if you want to be on the mailing list for this seminar, then please put your name and your email on this paper. Well, my name is Alexei Gorinov. You probably know this, but just in case. The email well, if you have any questions regarding the seminar or other questions, please use this email. Well, we unless there are objections, we will meet at 4:20 p.m. And there'll be two classes, so we finish at 7:20. What else? The final mark by default is 100% the mark for the final exam, but there might be well, if there are people who would like to give a talk, then there are certainly several side topics which are appropriate for talks. So please let me know. And the final exam will be a takeaway exam, meaning I will give people problems, and then they will have about a week to do those problems. Are there any questions? Okay, so again, if you have any questions, then please send me an email. So today there will be just an introduction. We will discuss the origins of the stable homotypic category and one of the definitions of a spectrum and examples of spectra, and basically this is it. So I hope we'll finish early. Okay, thank you. So let's remind ourselves of the Freudenthal suspension theorem. What is it about? And well, historically, this was the first indication that there is such a thing as the stable homotypic category. So suppose we have suppose we have two CW complexes with base points, and we are interested in the set of the base point preserving maps from X to Y, and there is a suspension map from the maps to X to Y to the maps from sigma X to sigma Y, where sigma denotes reduced suspension. Does the expression reduced suspension make any sense? If it doesn't, please let me know. Okay. And in general, this map sigma is neither injective nor surjective. It's just a map. But the Freudenthal theorem tells us two things. Firstly, the sigma is a bijection if Y is n-connected and X is of dimension strictly less than 2n plus 1, and a surjection if the dimension is exactly, if the dimension of x is exactly equal to n plus 1. Okay, well, those two n's and n's are easier to remember if we consider this example. Oh, by the way, n connected. Does this expression make any sense? If it doesn't, please let me know. Okay, so let's consider a simple example. Let's take x equal S3, y equal S2. Well, S2 is 1 connected. And S3 is of dimension 2 times 1 plus 1. So this map should be this map need not be an isomorphism, but it must be surjective. Let's look at S3. S3 is 2 connected. Very well. But on the other hand, 2 times 2 plus 1 is 5, which is greater than 4. So this map must be an isomorphism. And for the same reason, the next one is an isomorphism, and all the rest of them are isomorphisms too. Okay. We know this set, which is in fact a group. What is it? So what is pi 3 of S2? Say again?
Third homotopy group of S2.
Good, but what is it? Well, there's an answer. I didn't see who said it, but it's Z. How to prove it's Z? Yes. This is well. This is elementary.
Exact sequence of
yes, we consider the Hopf vibration. And the homotopy groups of S1 are very easy to calculate. Pi 1 is Z, and the rest of them are 0. In fact, this is the only sphere for which the homotopy groups are known. So what do we have? We have pi 3 of S2 goes to pi 2 S1, and this is 0, by 3s3. Well, we sort of know this is Z, and by 3s1, 0. So we have 0 on the right, 0 on the left, so the map in the middle is an isomorphism. And this was a big surprise in the 1930s when people just discovered homotypic groups. At first, the idea was that the homotypic groups are the same as homology groups, and this turned out to be not quite the case. So the surprising part is that the homotypic groups may very well be non-zero when the index is greater than the dimension of the space, while for homology groups this is well, at least for CW complexes, this is not possible. Anyway, what's this group? This one's a bit harder to calculate. I don't know any elementary way to calculate this group, but well, it depends on what exactly one calls elementary. Basically, to calculate this one, we would need we need some spectral sequences. For this one, we don't need spectral sequences. For this one, we do. Anyway, does anyone know the answer? Anyone? So this one is Z by 2Z, and so are the rest of them. In other words, the third homotypic group of S2 is not stable, but the fourth homotypic group of S3 is already stable. I'll shortly explain what this means. Are there any questions? So this example is useful to keep in mind if we want to remember the n's and 2n's in Freudenthal's theorem. If we take if we take a CW complex X and take pi I of X, no, let me put an n here. Okay, so I take pi n of X, the nth homotopy group of X. Then I apply the suspension map. I get the suspension map goes to pi n plus 1 of the suspension sigma x. Then I use the suspension map again. I end up in pi n plus 2, the double suspension of x, and so on. Now, by the Freudenthal theorem, this sequence will stabilize, meaning all those suspension maps are isomorphisms starting from a certain I, which depends on n and on x. Exercise. What is the I? It's an easy exercise if we assume Freudenthal's theorem. And these groups are called the stable homotopy groups. The stable homotopy groups of X, and as we will see, they form a homology theory. We will see what it means for a functor or a sequence of functors to be a homology theory. And initially, people thought that this would make these groups computable, but this turned out not to be the case. Stable homotopy groups are easier to calculate than just homotopy groups, but still it's still a very complicated task. For example, by looking at these calculations, we see that by 1 stable of S naught is Z by 2. Well, this table by naught of S naught is Z, which is which is sort of straightforward, and then one basically one has the answer for n up to approximately 100, and this is it. The rest of them are unknown. So it's despite the fact that stable is easier than unstable, they're both complicated. Very well. Are there any questions? So the Freudenthal theorem tells us that it would make sense to see what happens if we stabilize a space. Meaning we take a space and we want to identify it with its suspensions. What do we get? Well, we get the notion of a spectrum. Let's see what spectra are. A spectrum is a sequence of pointer spaces and maps from each space to the from the suspension of each space to the next space. It's not obvious that this is the right way to stabilize spaces, but after we see some of the properties of the categories of spectra, we will see that this definition makes sense. It looks deceptively simple, and we will need to do some work to convince ourselves that this is the right kind of objects to work with. Okay, so examples of spectrum. Well, the first example, the suspension spectra. What are these? We take xn to be a point for negative n, xn is the nth suspension of x for n greater than or equal 1, where x is just some CW complex. In particular, if we take x equal s naught, and by the way, I've already used this expression a few times, but what exactly is s naught? Yes. So, then the nth suspension of S naught will be just the n sphere for every n greater than or equal 0. Very well, so we we get what people call the sphere spectrum. Which plays an important role in the story. It's the unit of the standard of a natural product on spectra. Okay, so the suspension spectrum of a CW complex X is denoted sigma infinity of X, and then if X is S naught, we get the sphere spectrum. And the notation is well, the notation is simply S. Okay, well, are there any questions? Another example, which is probably somewhat familiar, the Eilenberg-MacLane spectrum. What are these? Well, first of all, the Eilenberg-MacLane spaces. So suppose we have an abelian group which we want to call pi. Has nothing to do with the circumference of the unit circle. It's just the notation people often use in this circumstances. Okay, pi. Then, using this pi, we can construct the Eilenberg-MacLane space K pi n. Does everyone know what this thing is? If not, please don't keep it to yourself. Let me know. Okay. Now, the okay, k pi n. Now, my claim is, well, here n is an integer number greater than 0. Well, there's a way to define k pi 0 just by taking pi as a discrete space, but we don't need this yet. Okay, so now I want to see what happens if I apply the omega functor to k pi n plus 1. Now, firstly, does this omega, let me draw it better, does this omega make any sense? Again, if I'm using notation which doesn't make sense, please let me know. Okay, so omega k n plus 1 is what? K pi n, yes. Okay, let's fix an equivalence. Let's fix an equivalence omega k pi n plus 1 with k pi n for all n greater than or equal 1. So let me write this again. Well, an equivalence goes both ways, but I wanted to go from k pi n to to omega k pi n plus 1. Okay, now I want to apply the sigma omega junction. So what do I end up with? I'll explain in a minute what this means. So what I end up with is a map from sigma k pi n to k pi n plus 1. This was an equivalence, but this one needn't be. It's definitely not true that the suspension of k pi n is k pi n plus 1. Okay, now does the expression sigma, okay, let's forget about sigma and omega. Does the expression adjunction make any sense? Okay, so there are adjoint functors. And we have two functors from, let's say, compactly generated Hausdorff spaces to, again, compactly generated Hausdorff spaces, which which are adjoint. Okay, I'll still have enough space here, so suppose x, y are compactly generated Hausdorff. Then even on the level of spaces, we have C Cx y is homeomorphic to C x omega y. Now, there is a couple of potential issues from point set topology, which are solved by taking the compactly generated topology whenever it may not coincide with the topology we're given. For example, we have the compact open topology on omega. Just in case, take the compactly generated version. Okay, same here. We have the product topology, the quotient topology of the product topology on sigma x. Just in case, take the compactly generated version. And this thing will become a genuine homeomorphism. Okay, does the expression compactly generated topology make any sense? It doesn't make sense for some people, and it does make sense for some other people. Okay, do we want to know what this is? It's a technical thing, and well, at least today I want to sweep it under the carpet. But if there are people who want to know but don't know, please let me know. So the important thing is that we have with an appropriate topology on the left-hand side and on the right-hand side, we have a homeomorphism of the topological spaces, not just a projection between the homotopy sets. Okay, very well. So if we believe this, then we can pass from a map from K to omega to a map from sigma K to the next K. And so we get a spectrum which is the result is the Eilenberg-MacLane spectrum, and it is denoted H pi. For reasons which we will see later. Basically, the cohomology theory given by the Eilenberg-MacLane spectrum is the same as the usual cohomology with coefficients in pi. Are there any questions? Now, we have seen we have just seen an important property of spectra. Let me give the definition. Suppose we have a spectrum. It's an omega spectrum if for all n the map, so we have a map from sigma xm to x n plus 1 by the sigma omega junction I get a map from xn to omega xn plus 1 and if all those maps happen to be homotopy equivalences, then X is called an omega spectrum. And one example is the one we've just seen, the Eilenberg-MacLane spectra. As we will see, the reason omega spectra are so important is that these are the fibrant objects with respect to a certain natural model structure, and moreover, these objects will be will also be cofibrant if we if we pay enough attention to how we choose the maps. Basically, here I just said choose an equivalence. Well, if we're careful enough with those equivalences, then with these ones, then the omega spectra will be fibrant and cofibrant, and basically from the viewpoint of the homotopy theory, it's as good as it gets. Any questions? Well, the last example for today. So, blah, 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 number 3. The Thom spectrum. Well, let's define just one of them. Basically, the one that Thom himself showed it to be a sum of the Eilenberg-MacLane spectra with possibly with shifts. Okay, the spectrum MO, what is it? Well, I need to define the spaces. So I need to define the space MO of n. What do I do? Well, I take MO of n to be the Thom space of gamma n. Very well. Now, does any of this make any sense at all? Let's see. So firstly, what is gamma n? Okay, now gamma n is the universal rank n real vector bundle over BON, where BON is the classifying space of ON, which is the same as the Grassmann manifold Gn of R infinity. Now, I've written something, and it looks nice, but does this explanation explain anything? If it doesn't, please let me know. So we take the Grassmannian of n planes in R infinity, and over it there is the universal or tautological rank n vector bundle. Well, the word universal means that every other vector bundle of rank n over a paracompact Hausdorff space is the pullback of gamma n under some map from the space to BON, and two vector bundles are isomorphic if and only if the maps from the base into BON are homotopic. Okay, do I need to write down what I've just said, or not really? Okay, so now we know what gamma n is. Gamma n is the tautological vector bundle over the Grassmannian of n planes in R infinity. Very well. Now, what's the Thom space? Does everyone understand, know what the Thom space is? Okay, so let me remind everyone what let me remind everyone of the Thom spaces. Suppose we have a real vector bundle with a metric. This means that there is a Euclidean metric on each fiber, and this metric varies continuously depending on the fiber. So the Thom space of E is the same as B of E by S of E, where B of E is the corresponding bundle of unit disks, and S of E. Okay, since disk begins with a D, let me write D. I could have said balls, and then B would be the right abbreviation. Anyway, we take the unit disks, which is the space of all vectors that have length less than or equal 1. Then we have the unit spheres. We take the unit disks, the space of all vectors of length less than or equal 1, and collapse the space of all vectors of length precisely 1. And we get something which is called the Thom space. And why is it called the Thom space? Well, if we think a little,
One question, please. How can we define Thom space for infinite dimensional case, as we are there with gamma n?
There is still a metric on gamma n. Well, no, there's never a canonical metric, but there is a metric. Let's think of gamma n as a bundle over Gn R infinity. Let's take some Euclidean metric on R infinity. What is R infinity? R infinity is the direct limit of Rn's. Well, take for example the following metric: the sum of the squares of the coordinates. This makes sense for elements of R infinity as well, because all elements have finitely many coordinates. And let's look at the fibers of gamma n. The fibers of gamma n are all possible n-planes. Well, we just restrict this metric to each n-plane, and we get a metric on the bundle. So even if the base is infinite dimensional, it doesn't matter. We often have metrics on the resulting bundles, and basically by using partitions of unity, we can construct a metric on every vector bundle over a Hausdorff paracompact space. So this condition isn't really too onerous. Let me just say one thing which explains the word Thom. We have the Thom isomorphism theorem. Which goes from the cohomology of the base with coefficients mod 2 to the cohomology of the total space mod the space of non-zero vectors again mod 2. This is the Thom isomorphism. And the point of using the Thom spaces is that this this relative homology, cohomology group is the same as the absolute but reduced cohomology group of the Thom space. Okay, so now we know what the Thom space is, and it's a standard exercise to show that up to homotype equivalence, the Thom space does not depend on which metric we use. Very well. So now we know what those Thom spaces are. Now we need to construct a map from the suspension of MON to MON plus 1. How to construct this map? Suppose we have two vector bundles. Real vector bundles. Well, the usual precautions apply. Let's assume that x1, x2 are paracompact Hausdorff. Then my claim is, well, let's take the direct product of the total spaces. The direct product of the total spaces will be a vector bundle over the direct product of the bases. No surprises there. But my claim is the resulting Thom space is the wedge of the Thom spaces of the two. No, not the wedge. The smash of the Thom spaces of the two bundles. Does the smash product make any sense? If it doesn't, please let me know. I think we'll finish in 5 minutes. So, we have the smash product, and Now something will happen. I start with the reduced suspension of MO, and I want to map it to MO plus 1. Well, firstly, the reduced suspension is S1 smash MON. Now, what is S1? S1 is the Thom space of the trivial rank 1 bundle over a point. No surprises there. Okay, and what is MO? Is the Thom space of gamma n. And so here we have a wedge of 2 Thom spaces. Well, by the exercise we know that the whole thing is equivalent to the Thom space of basically to the Thom space of gamma n plus epsilon, where epsilon 1 is the trivial rank 1 bundle over the Grossmanian. More precisely, we have to take the direct product of the trivial bundle over a point and the tautological bundle over the Grossmanian. Well, let's take the direct product of a point and the Grossmanian. What do we get? We get the Grossmanian. And what happens on the side of the vector bundles? Well, we just get an extra trivial rank 1 vector bundle. And now we have a bundle of rank n plus 1 . We know that this bundle has a classifying map from BON to BON plus 1. So we have a fiber-wise map of the vector bundles, which induces a map of the Thom spaces. So so we get a map from sigma MON to the Thom space of gamma n plus 1, which is MO n plus 1. And the resulting sequence of spaces and maps is called the Thom spectrum of the Thom spectrum MO. And in the same manner, one defines the spectrum MU, MU, MSO, MSU, MSB, and so on. And all these are called the Thom spectra. What's the canonical map between what? There's we have this vector bundle over BON. So by general nonsense, there is a classifying map. In this particular case, there's an explicit construction of the classifying map, which I've forgotten, but it's not too difficult. But we don't really need it yet. For today, it suffices for us to know that this map exists. Are there any other questions? Very well. So this is all for today, and we'll meet next week and start doing some technical stuff, which today was more of an introduction.